Well, welcome everyone. We'll be sharing in the same time two courses, Adaptive Computing and Nonlinear Physics and Complex Systems 2. The first one is specific for students of the graduate program of computer science, and the second for the graduate program in physical sciences at the National University in Mexico. But it's open to all students worldwide. That's why we're doing it in English. And the lectures, they're for a general audience. So let's say there are no prerequisites. So over the years, we've had a wide variety of students, doctors, artists, economists. But then for projects and homeworks, then it will be a bit more specific with more programming for computer scientists and more, let's say, physics and statistics for students of the graduate program in physical sciences. And let me share my screen. Now, I'll give you today first some information about the course and then some philosophical aspects about the topics we'll be dealing with over the semester. So, yeah, well, before everything and while people join, it would be useful to have a round of introductions. So I like this painting by Paul Gauguin, which is in the Boston Museum of Fine Arts. Where are we going? Who are we? Sorry, where do we come from? Where are we? Who are we? Where are we going? So if you could very briefly tell us that. Where do you come from? Basically, what have you studied before? Who are we? What are you doing now? Whether studying or working or looking for something? And where are we going? It would be, where would you like to see yourself in 5 years? So I don't know if everyone sees the same order of people that I see on Zoom, but anyway, let's try to do it in that order. So Luis, could you please begin? Luis L, you're on mute. Oscar, can they unmute themselves or? Or maybe he's not available. Victor Manuel Sanchez.
Hi. Well, I come from the Mexico City. I'm studying in the FES Aragon. I think I say that in English. Studying the computer engineering. Where are we? Well, in this moment, my only purpose is studying the. I don't remember that.
If you prefer to say it in Spanish, it's okay.
Thank you. Actualmente solamente estoy estudiando la maestría, no me encuentro trabajando. Y por último, ¿hacia dónde quiero verme en 5 años? Bueno, para este momento me gustaría estar trabajando sobre esta área, que es en la inteligencia artificial. Me encantaría seguir trabajando en específico en el área de del cómputo evolutivo.
L. Roca.
Hi. Hello. I study my PhD on electrical engineering, but the reason why I'm taking the course is to study a little about hurricanes And my proposal that I have for you is to work in the visibility network applied for the annual activity of hurricanes. Okay, thank you.
Yeah. Odin?
Hello. Hello. Hello, I'm Odin. I'm from Spain, and I'm a biologist, half mathematics, with a lot of interest in artificial life. So I'm doing a postdoc now in the UK, and trying to find any other postdoc, but now more into evolutionary computations and artificial life, basically.
Yeah. Where in the UK are you now?
I live in Aberystwyth, but I work in Norwich. Aberystwyth is in the middle of Wales. Nobody knows it really.
Yes. Well, I know it's Wales, but yeah,
Okay,
I haven't
okay.
been there, but know some people from there. Yeah.
Okay.
Okay, welcome. Heriberto?
Hi, greetings. My name is Heriberto Avelino. I'm a linguist. I have a PhD in linguistics. I did a postdoc on cognitive brain sciences also. Who are we? I'm a researcher at the National Institute of Anthropology and History in Mexico. And then what I do phylogenetic analysis of languages and population genetics combined. Some research on brain and language interaction. And where are we going? So, well, I hope I can survive these pandemics and in 30 years retire. Thanks.
Okay. Francisco Bautista.
Hola, soy Francisco y soy estudiante de doctorado en física. Mis líneas de investigación se centran en los sistemas complejos y espero que este curso me pueda aportar bastante en la computación adaptativa para tener un panorama más amplio de los sistemas complejos.
Okay. Mauri Diaz.
Hi everyone, I'm from Mexico. I study physics in the National University of Mexico. In fact, I'm taking my last semester and my thesis is about mathematical biology. In 5 years, I want to delve into complex system research because I have a fervent passion for complexity science. And well, that's it.
Thank you. Raúl Galindo. Olivia Sanchez.
Hello, my name is Livia. I am from the School of Psychology at UNAM. I am interested in this course because I think it should be taken account in psychology, this approximation.
Thank you. Martín Ortiz.
Hola, buenos días. Soy Martín, estudio en la maestría en la Facultad de Ingeniería y en la UNAM. El principal motivo por el que estoy aquí es porque quiero expandir mi conocimiento. Actualmente estoy trabajando con redes inteligentes y smart cities. Entonces quisiera agregar por este lado un poco de conocimiento.
José Ruiz Galloso.
Hola, bueno, yo estudié la carrera en física aquí en la UNAM. Actualmente estoy estudiando la maestría también aquí en la UNAM en el área de física estadística y sistemas complejos. Y pues en el futuro me gustaría seguir estudiando en esta área, ¿no? Hacerle el doctorado.
Muy bien. Daniel Rubio.
Hi, my name is Daniel. I come from the Masters in Physics in the UNAM, and I'm studying mobility and random walkers in networks, and I want to be doing that in the future.
Hola, Flavio.
Hi, good morning. I'm Flavio. I'm a civil engineer. Actually, a PhD student at in management studies at the National Polytechnic Institute. I'm trying to work on a PhD project dealing with project management and complexity. Thank you.
Gracias. Mario Lorenzo Flores.
Hi, good morning, everyone. I'm Mario Flores from Mexico City. I work for the Ministry of Education here in Mexico. I'm interested in complexity and professional development. And maybe in 5 years I'll be retired, but by now I'm quite interested in complexity. Thank you.
Thank you. Sofia Mihelian.
Hi, I am Sofia Megalian. I studied physics at the UNAM, and right now I'm doing my master's degree in the EMAS, and I'm doing the master's in computer science and engineering. And my main interests lie in the line of complex systems and fluid dynamics. My goal is to apply a little bit of artificial intelligence into solving fluid dynamics equations. Thank you.
Alejandro Puga.
Hello, everyone. I'm a professor at the physics department in La Universidad Autónoma de Zacatecas. I took this course because it's really interesting for me, and in 5 years, I want to have a very consolidated area on complexity in my university. That's what I am here. Thank you.
Thank you. Marina Menes. Marina.
Yep, sorry. Good morning. My name is Marina Menes. I am an experimental psychologist interested in temporal learning, and I am here to know more about this approach. So I think it could be good for my research, and I work here at UNAM.
Great. Thank you. Adriana?
Hi, my name is Adriana. I come from the chemistry faculty at UNAM. I studied pharmaceutical chemistry, and now I am working as an entrepreneur on the medical devices area. And in 5 years, I see myself working in the biotech and medical device industry. So I hope this class can help me understand these complex systems.
Thank you. Osvaldo Palacios. Leonardo Ledesma.
Hi everyone, my name is Leo. I'm PhD student in computer science at UNAM, Mexico. I have working with convolutional neural networks and bioinformatics. I am here because I want to know more about the different methodologies in artificial intelligence.
Good. Luis Ramón Moribe.
Good morning. Hi to everyone. My name is Luis Ramón. I am from Mexico City. I have a bachelor's degree in statistics. Now I am a master's degree student in applied mathematics at the Metropolitan University. My interests are data science and complexity science. Now I am working in topological data analysis applied to complex network. I would like learn more about adaptive computing, such as agent-based model, complex networks. Yes, thank you. Nice to meet you.
Yeah, we'll see some of that. Michelle Reyes.
Hello, I'm Michelle. I study physics in la UNAM, and right now I'm studying the Master of Computer Science at the UNAM too, and I'm working as a data scientist in a marketing company. So in 5 years, I hope to keep working as a data scientist, but with more knowledge.
Good. Lucrecia Lombardi.
Hola, buenos días. Yo soy estudiante del posgrado en sistemas complejos aquí en la UNAM y recién el semestre pasado fue mi primer contacto con programación en Python. Entonces estoy muy interesada en aprender todo lo que pueda acerca de programación. A mí me interesa los modelos para describir dinámicas espaciotemporales de sistemas biológicos y todo lo que tenga que ver con el sistema nervioso. Entonces, en los próximos 5 años quisiera seguir aprendiendo todo lo que pueda acerca de redes neurales y distintas formas de modelar estos fenómenos. Muchas gracias.
Muy bien. Wealth. It's useful if you put your full name. Rodin.
Sí, hola. Soy bioantropóloga. Actualmente estoy terminando mi postdoc en el IMAS y estoy interesada en este curso porque dentro del postdoc aprendí un poco de este enfoque que tiene que ver con la complejidad y me gustaría complementar lo que yo aprendí durante toda mi carrera, licenciatura y maestría, que es la parte micro, y en algún momento unir las dos áreas para entender la complejidad del ser humano.
¿Con quién estás trabajando en tu postdoc?
Ay, perdón, con Gabriel Ramos.
Sí. Muy bien. Hugo Cardosa.
Hi, I'm Hugo Cardosa. I come from Mexico City. I study computer engineering and applied mathematics. I studied, now I'm a software engineer at Google, and I'm trying to figure out where I want to be in 5 years. I like this kind of topics. I'm looking forward to learn from this.
All right. Armando Rangel.
Hola, buen día. Yo soy estudiante de doctorado en economía y tengo líneas de investigación sobre teoría del comportamiento, con Kahneman, por ejemplo. Y también estudio física y matemáticas, entonces estoy tratando de mezclarlo para análisis de políticas públicas. Entonces yo creo que la modelación del curso me puede ayudar, ¿no? Buen día, gracias.
Sí. Muy bien. Mauricio Telles.
Hi everyone, my name is Mauricio. I am from Mexico City. I am currently a political science undergraduate student at UNAM. I want to learn more about complex systems, epidemiology, and cybernetics theory for my thesis. And it's a pleasure to be here. Thank you.
Domingo Islas.
Hola, buenos días. Soy estudiante de maestría en la UNAM. Me gustaría seguir. Bueno, el semestre pasado llevé el curso de Sistema Complejos 1. Quisiera seguir aprendiendo sobre este tema porque quiero aplicarlo en mi tesis de maestría sobre el ajedrez y aplicar ecuaciones y esta metodología de sistemas complejos en ese programa. Nada más.
Muy bien. Sadid Sánchez.
Hola, buenos días. Soy Iván Sánchez, de la Ciudad de México. Soy biólogo y bueno, me interesa mucho la teoría de cambio sobre sistemas socioambientales y adaptación al cambio climático relacionados con vulnerabilidad hídrica.
Muy bien. Luis Barbosa, estamos haciendo una ronda de presentaciones y pudieras decir qué estudiaste, qué estás estudiando, dónde te gustaría estar en 5 años.
Hola, ¿qué tal? Buenos días, muchas gracias por aceptarme. Yo ya no estoy estudiando. Yo finalicé la maestría de Matemáticas Aplicadas en la UAM Iztapalapa. Hice la tesis fue de modelado de enfermedades infecciosas, la persistencia, la extinción y la invasión de una epidemia. Esto fue en alrededor del 2010. Hoy ya me encuentro trabajando en el Banco de México y estoy interesado en estos temas de la complejidad para abarcar diferentes problemas, ¿no? Y acá hacemos un poco de modelado, pues un poquito de sistemas más como informáticos y de información y procesamiento masivo de datos. Y pues estoy aquí tratando de seguir entendiendo más acerca de lo que es la complejidad y principalmente pues es que me quedan muchísimas dudas, ¿no? Entonces por eso me interesa en tomar esta clase.
Muy bien. Well, I'm Carlos Gershenson. I studied computer engineering at the Fundación Arturo Rosenbluth. I did a master's in evolutionary and adaptive systems at Sussex University in the UK. My PhD was on design and control of self-organizing systems at the Free University of Brussels. Then I did a postdoctoral stay at the New England Complex Systems Institute, and I have been a research professor at UNAM since 2008. So let's say in our group, the Self-Organizing Systems Lab, we try to understand complex systems in order to better deal with complexity that's pervasive in our surroundings from a theoretical perspective, but also with applications and also following their philosophical implications. And I would like in 5 years to have developed another project that has real world impact. I mean, we'll tell you about the project that have been successful so far, but let's say it's more difficult than one might want. So I hope that in 5 years we can tell about more recent projects as well. So the syllabus for the course, let's say it's without much detail. We'll see a bit of systems, its history, different concepts that have been put forward in general systems theory. How is this related to computing and also to philosophy? Adaptation, it's a very broad subject. We will see control and feedback, and that, of course, takes us to cybernetics and concepts that were posed in cybernetics. We will stress on the difference between stationary and non-stationary spaces, which is basically problems that don't change. So once you find the solution, you're done. And problems that do change either by their inherent nature or by your own solution, it will change the problem. And then you need adaptation. And that's why it's called adaptive computing, the course. So how do you design computations that will adapt to unforeseen changes? And there are many techniques that we'll see. We also see what's the differences and similarities between chaos and complexity and stigmergy. which let's say it comes from insect ethology, but can also be applied for developing adaptive algorithms. And we'll see examples and applications that use self-organization in order to build adaptive systems. So, for example, synchronization in fireflies, which can be said to be self-organizing, how it can be modeled abstractly as oscillators, and how it can be applied to communication systems. And foraging, which it's a natural phenomenon, but it has been used for inspiration to ant colony optimization and also for public transport regulation and other adaptive systems. Swarms, it's another natural phenomenon that has been used to inspire particle swarm optimization. Flocks can be seen as an inspiration for self-organizing traffic lights that adapt to changing demands in traffic. In a similar way, self-organizing bureaucracies, they adapt to ever-changing demands in the system. Public transportation systems and equal headway instability. It's some of the work we've done recently, and also in crowd dynamics. We also see a bit of networks because they are very natural formal tool to model complex systems, because the elements of the system are nodes and the interactions can be represented with their links. So we'll see a short introduction to network science, random Mooreland networks, which are generalizations of cellular automata. And with them, we can study robustness, resilience, anti-fragility, modularity, anti-modularity, redundancy, degeneracy, many properties that have to do with robustness, but also with adaptivity in complex systems. And there will be final projects, so there will be advances on these final projects that you should be developing over the semester. I'll tell about the final projects in due time. So the classes will be Tuesdays and Thursdays at 10:30. They will be on this Zoom channel. If I understand correctly, for Thursday, we will change the password. So check the Google Classroom for the new password. And usually every month, the password is changed. You can also go to the C3 YouTube channel, and there you can watch again the lectures, the archive. For some reason, you don't have access to Zoom, you can watch straight on YouTube, but then of course you cannot interact. There will be like 3 classes that this channel for the C3 will be busy, but then we can just use my personal Zoom channel, and then the video will be uploaded to the YouTube. So those days they won't be streaming, and I will send you with time the precise connection details. So we'll have lectures like this and seminars and discussions. So in some cases, we will, you should read a paper, and then over class we will discuss the paper on different topics. And the coursework, it involves, let's say, the homeworks. Some of these are summaries or your own opinion about topics we discuss in class or about the papers you read. For computer science students, there are programming projects, and for the physical science students, there will be some other homeworks. And the final project, it's the idea is to do something that could be presented at national or international conference. And it should be a text, let's say about 8 pages long, showing, let's say, with a structure, introduction, background, methods, results, conclusions, bibliography, with some figures. If you're studying computer science, then probably there should be some software that you're using to find your results. In the physical science, it might or might not be with a simulation. if you don't know how to program or don't have mathematical background, don't worry. It would be just an essay. Let's say advancing some of the concepts that we see in class. Also, if this final project can be seen as a stepping stone for another project of yours, either personal or part of your thesis, that is also valid. We will be using Netlogo, so if you don't know about it, you can download it for free on that webpage. And you can just start playing with it. There are plenty of tutorials. If you don't program, don't worry, you won't need to learn how to program. But if you feel like challenging yourself, then just play with it, and it's really easy to start programming in Netlogo. And also there's a possibility to present some of the final projects at international conferences, like the complex systems. The conference on complex systems will be hybrids in Palma de Mallorca and online, so it could be presented either going there or presenting remotely. Artificial Life conference will be well, it's a bit short because the deadline is this month, but it will be online. And well, there are plenty of conferences, and it doesn't have to be this year. It could be presented next year. Also, we've had several projects with government or with industries or with international colleagues. So if you're interested, we can also work on one of those projects that we'll speak about over the course. Yes, Celia?
Yeah, my question is if my interest about the hurricane activity is suitable subject, and also I am interested, but indirectly, with mobility in Mexico City.
Yes, both are suitable. Yeah.
Okay, thank you. Then maybe I can try.
Yep. So let's say the main course is ac.gershenson.mx, but let's say most of the activity will be on Google Classroom, and most probably you are already enrolled there. If you haven't, please enroll there. And the easiest way to find me is by email. So it's just, my email is just cgg@unam.mx. Okay. Are there any questions of the course? If you have them later, you can also post them on Google Classroom or send me an email. Okay, so now I want to share with you some ideas that are published in this paper, the implications of interactions for science and philosophy. And this because it's like the philosophical background or the philosophical motivation for the course, like why is it relevant to study complexity and adaptive computing. So science, since it's called science in times of Galileo, Newton, Laplace, Descartes, it has been reductionist until relatively recently. And this means that the scientific methods tries to separate and simplify in order to predict. And this has been very successful. However, this does mean that reductionism doesn't have limits. So we might wonder what are those limits and what to do if we want to go beyond them. And it has been very effective because thanks to reductionist science, we have built computers, we have built satellites, missions to Mars, robots, computers, internet, all of these have managed to isolate problems. And then once you find a solution, then you can combine it with solutions to other problems, and like that, incrementally build more and more complex systems and more complex technologies. And just to mention one of the effects of this in medicine, in 100 years, life expectancy worldwide was duplicated. Now it's going down again because of the pandemic, but let's say, let's hope that it will start going up again soon. And actually, well, it was so effective that before most people would die of infectious disease. And since this disease have a single cause, let's say a pathogen, either a virus or a bacterium or a parasite, fungus, that causes that disease, then there are ways to limit that cycle of disease, either cutting the spread, the contagion, or attacking the pathogen, or limiting somehow the pathogen's life cycles. Well, viruses don't have life cycles, but well, it's reproduction cycle, and that has led that in most countries, well, in most developed countries, most people die now of degenerative disease like cancer, cardiovascular, hepatic, and so on. And these diseases are complex in the sense that they have multiple causes. So first of all, it's difficult to limit their spread because there's not like a vector that kind of gives you the disease. There are many factors, and it's difficult to consider all of them in parallel. And also, well, let's say, reductionism has been limited in treating this type of disease. So, what is complexity? I mean, we will see more about it in the next class, but just to give an idea, it comes from the Latin plexus. Etymologically, so it means interwoven. Equivalent word in Sanskrit would be tantra, which is a thread. A fabric. Sutra is thread. Tantra is fabric. So it's like many things related to each other. So when do we have complexity? When elements are difficult to separate. Why would they be difficult to separate? Because they have relevant interactions, and these relevant interactions determine the future of other components and therefore of the system. Therefore, reductionism is inadequate because reductionism precisely tries to isolate components and neglects these interactions. And if the interactions are relevant, then reductionism will not give you the whole picture. So this novel information has several consequences given by the interactions, and this is what we will be exploring today. What's the effect of this new information that is present due to interactions in complex systems? Well, first of all, it limits your predictability, and since complexity is everywhere, then let's take one step at a time and see all the implications that this has for our worldview. But before that, let's just mention that in philosophy, there's a distinction between epistemology and ontology. Epistemology studies how we know things. So you could say it's like how we describe or we perceive the world, considering its subjective nature. And ontology attempts to describe the world independently of an observer, how things are in themselves. However, even ontology is epistemological because the moment you name something, then you're already describing it from your own perspective and putting a label and making an abstraction. So my claim is that interactions are as real or unreal as matter as energy. Not to fall into the debate of what's reality and what isn't, let's just say that interactions can have causal influence on matter and energy. However, in traditional physics, interactions are neglected, and traditional physics, reductionist physics, assumes that the only real things in the universe are matter and energy. Therefore, if you have a full description at the physical level, then you can derive everything else. And I don't think that's correct. So an alternative epistemology would be based on information, and in another class we'll go deeper into that epistemology. But let's go to the implications of considering interactions as real, or basically as having a causal influence on the physical world. Well, first of all, it renders reductionism obsolete, because reductionism assumes that the whole can be described from the description of the parts. And then if you go to the lowest level, that say we don't really know which one is it, because it's the word atom means non-divisible in Greek, but then we were able to split the atom, and then let's say elementary particles were considered to be elementary. Then it turns out that nothing tells us that they cannot be described in terms of even simpler components. The limit is that in order to study smaller and smaller phenomena, we need higher and higher energies, and we cannot harness such energies so far. But anyway, the idea is, okay, we go to the lowest level, and once we have a theory of everything, we'll be able to describe everything. But then, since we have new information produced by interactions, we have emergence, that we'll also speak more about this on Thursday. And this leads to computational irreducibility. And we will also speak more about computational irreducibility. This means that you cannot, basically that the whole is more than the sum of its parts. Basically that you cannot derive a system from describing its components precisely because of the new information that is produced by interactions. In other words, you need to wait until that information is produced in order to have a full description of the system. And then, let's say, another implication that, let's say, that's less accepted by the community would be to speak about downward causation, meaning that this new information can have a causal influence on the lower scales of the physical realm. Well, I'll give an example in a little while. So another implication is non-materialism. So materialism assumes that only matter and energy are real, and all the rest are epiphenomena. So let's say social norms, biological interactions, all these are, let's say, useful because we can describe phenomena at that level, but reductionism tells us that, in fact, let's say it's just quarks following the laws of physics. But then this leads to a dualism because we cannot describe meaning in terms of matter, in the sense that meaning is arbitrary. And I mean, Wittgenstein noted this already almost a century ago. And since meaning is arbitrary, then you cannot derive meaning from the, or let's say you cannot, you cannot derive the meaning of a signal from the symbol that carries that signal, because the same symbol can carry different signals or different meanings depending on the context. And precisely that's what codes do. They encrypt some meaning into something that looks like garbage or like noise, and then you try to decrypt it, or let's say make it difficult for others to try to decrypt it. So if you have only the laws of physics, you cannot really get to meaning. And let's say we can speak not only about meaning in linguistic terms, that would be semantics, but also in biological terms. Like we can describe, for example, the behavior of a bacterium that avoids a harmful environment and moves towards a glucose gradient, that those signals have a meaning for the bacterium because it has an effect on its action. And let's say we can also describe the goals of the bacterium that would, let's say, interpret those signals with a particular meaning for the bacterium, and the same for all animals and also for some artificial systems. So one example about how interactions can have a causal effect on matter and energy is with money. So I think we would agree that the value of money is not physical. I mean, you cannot derive from gold atoms that they are valuable or that they will be exchangeable, or from cacao seeds atoms, or from the subatomic particles of 500 peso bills, or from the bits in some server that have your savings from your bank account. Let's say, how do you distinguish those bits from some funny cat videos? So, I mean, the meaning or the value of money is arbitrary. However, it has a causal effect on matter and energy. And just look at a building. It's made of matter, and it required energy to organize the matter in that building. But even so, imagine you have a full description at the subatomic particle level of a mountain. You wouldn't be able to predict that some humans will come and extract minerals from that mountain. And they're not breaking the laws of physics. It's just new laws that require money, because, of course, without money, you cannot convince people to go and do that. And then, let's say, there's a transformation or an effect on the matter of the mountain, and it transforms into different products, let's say a building. So that's one example of interactions being as unreal or real, however you want it, as matter as energy. So an alternative would be an epistemology based on information that we'll see in another class. So Heriberto writes on the chat, I will contend a broad notion of reductionism for characterizing past science. In a nutshell, Newtonian laws and the ethos of general physics, for example, is to account for laws that govern the universe. How can this be reductionist? So they're reductionist in the sense that the same Newton's laws, well, let's say perhaps the best example is Laplace's demon. So Laplace made a thought experiment and assumed, well, the particles in our universe, I mean, they still didn't have quantum mechanics in those years. So they assumed that the elementary particles would follow Newton's mechanical laws, Newton's laws of movement. So the assumption is that if a higher intelligence, a demon, would have all the positions and momenta of all the particles of the universe at a certain moment, it would be able to know all future and all past, because Newton's laws are reversible. However, in mid-20th century, we learned from thermodynamics. I think it was late 19th century. The physicists will correct me when thermodynamics became, let's say, mature enough to notice that many systems are dissipative. This means that you can be in the present and have multiple potential pasts, so you basically lose information in time. So therefore, even let's say if as you have Newton's laws, which are reversible at the micro scale, at the macro scale you lose that reversibility in thermodynamics. That's also related to Maxwell's demon. Yeah, Laplace's demon and Maxwell's demon. Yeah, we need more demons in science. But then to predict the future from the current state of the universe, you also need to take into account interactions. And this is precisely the nature of complexity. Because first, with quantum mechanics, it was kind of seeing, well, there's non-determination, but it occurs at just the micro level. So let's say that was beginning of the 20th century, and kind of people ignore because, okay, we care just about the macro world and we don't have quantum effects. Well, they thought we didn't have quantum effects in the macroscopic scale, so we can ignore that. But in the 50s, well, let's say Poincaré already described phenomena that we would call now chaotic, but it was until the 1950s that it became widespread. And I mean, we will also see a bit more detail about chaos, but the idea was that if you have, even if you have all the information about the present, then because of chaos, which is sensitivity to initial conditions, the future might have diverging trajectories from this almost the same present. So therefore, since we will never have enough precision, your prediction is limited. But then again, some people might say, well, that's prediction in practice. In theory, you can have as much precision as you want. But so that was like in the 60s, 70s. But then in the 80s, when complex systems began to be studied, and this idea that I mentioned, computational irreducibility, was better formulated, then it became evident that if you don't consider that novel information that is produced by interactions, then you cannot describe the whole system. So that limits prediction. And that's why I mean that reductionism is limited in that sense. So we will see, because it doesn't mean that reductionism is useless or that we should throw it away. It means that we should be very careful in understanding when we're going beyond its limits. It's basically when things change or when you have complexity, which in the real world, one might say, well, it's everywhere, but it depends basically on the time scales. So for example, if the change is relatively slow, so it takes, let's say, years to change, and your system is evolving, I don't know, at the scales of seconds or days, then it doesn't really matter. You can kind of build new systems as the conditions change. But when the problem changes much faster than the system can adapt, then you will end up with obsolete solutions. And that has generated several problems in our modern world. Okay, so another consequence of interactions is non-predictability. So let's say the reductionism was so successful that many people assumed that the universe was predictable. So it was, if we couldn't predict something, it was because we hadn't found its laws, or we didn't have enough computational power, or we didn't have enough data. We just needed to work a bit more, and then we would predict everything. So psychological phenomena, and we are beginning to understand or to recognize the limits of prediction due to complexity. And it's precisely because of these new information that is generated by relevant interactions. So if there are inherent limitations to our predictability, then we need to build adaptive systems. And that's why we're having this course, how to build adaptive systems in computer science terms. Usually a computation, you have an input, then a computing process, and an output. But then during that whole time, nothing changes. So let's say the output is still useful. Then if during that computation things changed, very probably your output will be mistaken or obsolete, or something might have happened. So how do you perform computations that can take into account the possibility for change during the computational process? And that's what we'll see. So yeah, again, it's not that prediction should be thrown out of the window. It means that we should acknowledge when we have limited prediction and build adaptation to complement our lack of prediction or our limited prediction. Ideally, we would like to predict everything, but we are beginning to understand and accept that we can't because of the inherent complexity of phenomena. And then we will be better prepared to face this complexity if we complement prediction with adaptability. Another consequence is non-Platonism. By Platonism, I mean here that there's a single true description of the world, which means that all the others are wrong. Wittgenstein already told that all descriptions are made within language. But then in postmodernism, well, some postmodernist authors, they would say that, okay, there's no truth, so anything goes. But that's not also the case. And this leads to what I call the silly theorem problem. So for any silly theorem, let's say 1 + 1 = 3, you can find an infinitude of axioms under which that theorem is valid. Therefore, which are the valid axioms? Or how do you justify non-silly axioms? And let's say, being pragmatic is basically with experience. It's like whatever works, or let's say with experience, you justify your axioms. But there are limits to formal systems, and we will also go into the limits of formal systems in the course. And here there's an example. Imagine we have a ball, which is half white, half black. But we can only see a perspective to it. So actually we don't see a ball, but a circle. So if we ask what circle the color is, some people will say it's black. Some people will say it's white. Some people will say it's 50% white, 50% black. And we could go to holy wars trying to defend what's the real color of the circle. And if we do an exercise of democratic mathematics, not necessarily we will get better outcome, because if the majority of people are perceiving the sphere from the black perspective, then the majority will say it's black. So if we to, let's say, what the majority thinks, that doesn't mean that everyone is homogeneously distributed and therefore the average will be representative. So if we agree that different descriptions of the same phenomena can coexist in different contexts, then let's say we avoid conflict and we can have richer descriptions, because then we can say, well, from this perspective, it's black, from this perspective, it's white, from this perspective, it's 70% white, and so on. And then we can see which description is useful in which context. And like that, we will be able to contrast different descriptions, because we also don't want like, well, it's whatever color. No, it's not whatever color. We are perceiving it in this way, in this context, and in that way, in that context. and then you can make experiments that will validate different descriptions, but that doesn't mean that only one description is the true and all the others are wrong. And the same applies to everything. So finally, we have nihilism. So one consequence of reductionism is that if you can explain everything by a grand unified theory, then what would be the space for life, meaning, free will, art, love, and so on? So that might lead some people to nihilism, meaning that well, we are just epiphenomena, and everything is predetermined, even when we have the illusion of a free will. We don't really have choice over our own destiny. I disagree with that completely. I think that free will is real, but that's another topic. What we can say is that the new information that is constantly being generated by interactions, they can lead to new meaning. So there's always space for amazement, for being inspired, and there's no final description because of non-Platonism that will kind of take meaning from our lives. So we can have potentially infinite meanings for human life. And already the process of discovering what these meanings are is meaningful. So yeah, it's like, what's the meaning of life? It's discovering what's the meaning of life. Yeah, so an alternative would be meaningfulness. So just to conclude, reductionism isolates phenomena for convenience. It's not that it's wrong. It's that it's limited. So if we try to apply reductionism to a context where, let's say it's beyond its limits, then very probably we won't get the same results as in the context it was proposed originally. So since no phenomenon is isolated and everything is related, and just neglecting interactions will not remove them, then if we include interactions, meaning complexity, in our descriptions, then we will have less conflicts. We'll have better understanding of phenomena. We'll have better solutions to problems. And this also in line with Buddhist philosophy that says that the separation between subject, object, and action is artificial. And let's say, given all the evidence that has been accumulated in recent decades from complexity, it would be time to change our worldview. And let's say this is already going on, but it seems it takes a generation or two to finally sink in, or maybe more. So if you want to read more details about this, the paper is here. Also, I invite you to subscribe to Complexity Digests, which is a weekly newsletter that we edit already for several years, and it's the official news channel of the Complex Systems Society. So if you subscribe or follow us on Twitter or I think other social networks are down, but you can subscribe and get an email for free. You will get the latest papers and news events related to complex systems. So for the next classes, the next class we will see about complexity. If you haven't done so, please go to Google Classroom and enroll. Yep. And if there are any questions.
Sí, una pregunta acerca de las tareas que vamos a entregar. Ensayos y opiniones, ¿prefiere que las entreguemos en inglés o en español?
Como prefieran. Sí.
Ok, bien, gracias.
So the idea is that you will comment on the essays of your classmates, but I think we will have enough so that we can have both English and Spanish. So you don't need to do everything in English. And yeah, I don't mind if you do everything in Spanish.
Bien, gracias.
Any other question? Let me see the chat.
Yo tengo una pregunta, la voy a formular en español, porque no lo tengo. O sea, la idea también es abandonar un poquito el reduccionismo, pero a la vez seguimos partiendo de él, ¿no? O sea, no podemos tener un sistema que guarde toda la complejidad de lo que queremos llevar. ¿O cuál es el acercamiento ahí?
Yeah, I mean, when reductionism is suitable, then we should use it. But then when we are better considering interactions, then we should consider interactions. And also there's a bit of debate because, for example, from my perspective, network science is not reductionist because you are considering interactions. So you are not going into the isolating the components of a system. But then some people might say they have a different interpretation of reductionism, and basically they say that reductionism is abstraction, but then everything is an abstraction. The thing is what you abstract. And in reductionism, you separate in order to predict. And the abstractions that you do with network science, of course, you also simplify many things, but you don't remove the interactions. And you also, networks also allow you to have a multi-scale description. So you can go from the individual to the system and back, and so have some mesoscales like modules and subnetworks and things like that.
Okay, so it is safe to say that complexity and reductionism both are abstractions, but one you don't remove as much interactions. You try to keep as much interactions as possible. Okay.
Yes. That would be my interpretation. That kind of makes sense in everything I said. If you assume that reductionism is just making abstractions, then everything is reductionism, because we don't have full descriptions of anything. Yes, Elio?
Yeah, I got a lot of problems to try to move from to reductionists to holies. At the beginning, when I started studying the hurricanes, I began to doing some reductionists and then studying as examples just the hurricanes in the Atlantic. But later I was thinking that was a wrong way to attend a complex system. Then I thought that maybe it's more assertive to thinking, more holistic to thinking, beginning with the world activity of hurricanes, with the whole, and then study the parts. Then this maybe is right this way to move.
Usually in complex systems, we precisely move between scales. So we go from the description at one scale to another and then back and see how they complement each other. In the case of hurricanes, it would depend on how much hurricanes interact among themselves. So basically, if the description of an isolated hurricane is sufficient, I mean, I know that you can't predict their trajectory, but better said, if considering more than one hurricane in a let's say in a region gives you better, not even prediction, but understanding of a single hurricane, then it makes sense to go at the higher scale. If you don't gain any new information by including, let's say, multiple hurricanes in space and time, then the description of a single hurricane would be appropriate. Yeah.
Thanks.
So Odin writes, in that sense, information is contained in matter, the energy, and the interactions. We can extract can we extract also information of interactions from material objects? I briefly mentioned an epistemology I developed, which say traditionally, since let's say there's the perspective of representing everything in terms of matter and energy, then there have been attempts of representing also information and meaning in terms of matter and energy. And since this hasn't worked out, what I did was to do the opposite. Why don't we represent matter and energy in terms of information? And like this, you can have a description of the world that's based on information that includes matter and energy and information. And then you can start exploring the laws of information, of which physical laws are subsets or particular cases. And it's interesting because in matter and energy, you have conservation laws, but in information, you don't have conservation laws. So you can, let's say information can be created, destroyed, and transformed. And that gives you, so for example, economy, more and more our economy is driven by information. And you can see that the richest companies are tech companies, Google, Microsoft, Facebook, Apple, and so on. So they are dealing less and less with matter and energy as, let's say, before, car companies, petrol companies. So, I mean, this just highlights the relevance that information has taken in our society, but also the value of information is not correlated with the work required to produce that information anymore. In industrial times, more or less the value of of products was more or less correlated with the work that was required to produce those products. So, and therefore, in economics, it was suitable to use tools from physics, where you have conservation laws to describe economics. But more and more, they're becoming obsolete because you can create economic value out of thin air with information. And you can see it with the film industry, music, art, what creates or destroys value, it's almost arbitrary. So I think economics should also get rid of conservation laws because value is not conserved. It can be created or destroyed.
Yeah. But we observe information about what the mark they leave on the real objects, right? In the amount of money in the case of the economy, or in the living beings, and it's our way of observing, right? The effect of information and the interaction. So for you, all this connection is somehow, no? Like the information connects through the interaction, the different objects in any dynamical system.
Thank you. Yes. Heriberto?
Hi, very interesting. Thank you very much. I have a question and a point to make. So first, I see the exposition of reductionism more like a strawman didactic. Let's say, you may correct me on that thing, but then just for the sake of argument and building up on this, do you think that we can escape to reductionism in the sense that, okay, so I can accept that there is no static way of dealing with this, or is limited, but then even if we recognize and acknowledge interactions, how you feel about this sort of paradox or problem? Because naming interactions, so it doesn't solve the problem of reductionism in this sense. So even though you have a complex system or have some phenomenon, just for the sake of argument, you always will be short at least one interaction when you list all the possible interactions of this system. I don't know if I'm making sense of this. So, okay, so let's depart from the view that the parts make the whole, and you can explain something just like enumerating, listing the parts. But then if you shift to interactions, you always will be n-1 interaction, because interactions are, if not infinite, you cannot commensurate this. This is uncommensurable in that sense. So am I making sense of this? Do you get the point I'm trying to make?
Yeah. I think that the purpose of science should be updated in the sense that I'm not suggesting that, oh, now we include interactions and then we will be able to predict everything. It's like we won't be able to predict everything because of interactions, but in order to understand better phenomena, we need to consider them in order to be able to say how much can we predict and what to do for all the situations that our prediction is limited. So it's not to acquire knowledge, but to acquire knowledge about the limits of our knowledge. Yeah. So it's also to make us a bit more modest in our understanding, because sometimes we understand something and we assume that we can understand everything. And it's like, well, we understand only this in this context, and it's very limited and difficult to generalize.
Yeah, if I can just follow up this short thing. So you're talking about interactions, and you didn't use the term, but we can use factors or whatever. So, but you didn't talk about the hierarchy or a given scale of these interactions or elements in this aim to predict. Because I mean, I can imagine some problems that the very same elements and interactions may shift if the hierarchy of these elements or the interactions among them are changing. So, and gives you a completely different story. So can you elaborate a bit? I mean, if this sort of topic, so don't even bother.
Yeah. Yeah, I mean, I think we will see more about this along the course. Yeah, it will be like too ambitious to try to explain everything right now. Okay. Daniel?
Hola. I have a question, and you said that the systems generate information. And I think that's related with this property proposed by Wolfram, the computational irreducibility. And I would like to ask you how this has been proven, because I know that it's like an idea proposed by Wolfram, but I don't know if this has been proven by a numerical experiment or maybe by a mathematical construction, or what is the idea, a simulation. I don't know about this. I would like to know if you could explain me. Thank you.
Yes, I'll sketch the answer because I will use terms that would take time to explain. But let me just tell that it's also related to the decision problem of Hilbert, that Turing showed that it was not solvable when he proposed his Turing machine in the 1930s. So this is also related to the limits of formal systems, in the sense that, Hilbert was asking whether there could be questions or propositions in a logical system that could not be decided by, I mean, he didn't pose it that way, but we would say it now by an algorithm. And Turing showed that there were some questions that couldn't be decided. And the one he used was the halting probability. So it's basically the halting problem is that you have a Turing machine and you have an input and a program, and then it runs. And the idea is whether you can predict whether it will halt or not. And Turing showed that you can't. However, if you have enough information about a particular Turing machine, could be experimentally, then you can explore a very broad range of initial conditions and check that it halts and halts and halts. And then you can say, okay, this machine, this is the halting function. So Turing himself explored this and called, let's say, with an oracle, you can determine the halting function of a specific Turing machine. But then that will give you a new Turing machine for which the halting function is not known, is not decidable, unless you have another oracle about that machine. And in many cases, let's say it's just, let's say a program runs infinitely, and you cannot prove that it will never halt unless it does. So there are formal proofs that, let's say, it was before the idea of computational irreducibility was proposed. And actually, you don't need the idea of interactions to have this. But precisely when you have interactions, the effect is similar in the sense that the interactions, if they generate new information, even if you have an oracle, it becomes useless because you're generating new information. So the one interpretation of this computational irreducibility is that there are no shortcuts for the future. It's not that you cannot predict, especially in very simple formal systems where the rules are known and initial conditions are known and you can explore it exhaustively with simulations. It's just that there are no shortcuts, meaning that you cannot give an answer that is shorter than running through the program. So you need to go through all the intermediate steps so that all the information that's in the interactions in the intermediate states occur is generated, and that will take you to the future. And this is related precisely with interactions, and also it's related with chaos. And when we see networks, it will be clear because this has to do directly with the number of interactions that you have in a network. If you have relatively few interactions in a network, then you can predict things. And then there's no computation. Well, you can reduce things. Yeah.
Muchas gracias. ¿Existe la posibilidad de que nos pudieras compartir el paper del que nos hablabas de Turing? ¿O quizás solo
Turing 1936 uncomputable numbers.
Muchas gracias.
With an application to the untitled problem. Okay, so I'll see you on Thursday, and we'll speak about complexity. And in the meantime, feel free to use the classroom to comment things. I will post there some further links to if you want to go in greater detail. So see you on Thursday.